Very good afternoon, students. Good afternoon to all of you. Am I audible? Yeah, good afternoon, Sanika. Good afternoon. Good afternoon, Vaishnavi. Students, can you all able to hear my voice? Yes. So today I'm unable to turn on my video. Just bear with me. Okay, so let's start with the today's session. So yesterday I gave you one homework, right? So did you guys memorize that 3D series from Scandium till Zinc? Okay, can anyone unmute yourself and tell me those 10 elements in order without seeing anything? Can anyone? So who is going to say? One of you have to tell. You can volunteer to yourself, and if you are interested, you can just uh, type those that in the chat box, and you can start deciding those 10 elements in the class now. So who is trying? Going to try? Who is willing to say? Tanika has typed everything. Cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. Very good, my dear. Okay, very good. What about others? Vaishnavi and Vikas, Sakshi, Surya Gauta. What about you guys? Did you guys memorize? Some of you may feel shy, no, to say this. No issues. If you have studied, then it's good. Okay. If you have not studied, if you have not gone through, very good, Vaishnavi. Good. Scandium. See, instead of scandium, you have typed sulfur. Just take a note. It is a typographical mistake, I know. Okay. So, if anybody hasn't studied those elements so far, so try to memorize at least today. Okay. So let's continue with the yesterday's session. So yesterday we have discussed about the oxidation state and standard electrode potential concept, right? So today I have to continue that standard electrode potential, and after that we will discuss about, sorry, yeah. So after that we will discuss about some of the stability and magnetic properties, formation of colored ions, complex compounds, catalysts, interstitial compounds, and alloy formation. Okay. So once we complete that standard electrode potential topic and the stability, we will move on to the next general property. Got it? So moving on to the next slide. So here in this slide, we are going to discuss about the higher oxidation state stability. Okay. So first we are going to discuss for halides, and then we will study for oxides. So you can see a tabular column in front of you in the slide, okay, in the screen. And if you look into that, titanium, vanadium, and chromium. So these three elements are existing in their highest oxidation state. Okay. But in all the three cases, in most of the thing, that halogen is a fluorine. Halogen is a fluorine. So only fluorine containing metal atoms, metal ions, they are existing in their highest oxidation state. So if I have other than fluorine like chlorine and iodine means, so those elements are not existing in their highest oxidation state. It is due to the highest bond enthalpy for fluorine. Okay, suppose if I take this chromium hexafluoride, so what is the structure of, just a second. Sorry. Yeah, sorry, my dear. Yeah, so the structure is CrF6, right? Chromium hexafluoride. So you all know that the size of fluorine is very, very small. Size of fluorine is very, very small. So the small sized atom will form a very strong bond between its metal. Okay, between chromium and fluorine, the bond energy, bond strength will be very, very high. So if the bond strength is very high, then the energy required to break that bond, which is called as bond enthalpy, it will also be very, very high. Okay, so we cannot able to break this particular bond easily. Means if we are not able to break a bond easily, means then that particular molecule is highly stable in nature. Okay, so because of the very small size, the size of fluorine, the metal in their highest oxidation state is formed with fluorine. Got it? Then when you look into manganese compounds, so we have manganese tetrafluoride, trifluoride, and we have dihalides also. Okay. And in all these cases, the manganese, the highest oxidation state of manganese is +4 only. Highest oxidation state is +4 in case of MnF4. Okay. But the manganese can exist in its very highest oxidation state, which is +7 in one compound, and that compound is MnO3F. Okay, MnO3F, oxyfluoro compound of manganese. So in this compound, if you calculate the oxidation state, so let me take this manganese as X, and for each oxygen, -2, -2, -6, and for each fluorine, it is -1, which will be equal to 0, and X is equal to +7. So in this particular compound, manganese is existing in there in its highest oxidation state. Okay. Then if I go for iron and cobalt, if I go for iron and cobalt, both of them are existing in their very, what to say, highest oxidation state, which is +3. So for iron also it is +3, and for cobalt also it is +3. So only the early transition means titanium, vanadium, chromium. So they are existing in their outer highest oxidation state in its fluoride form. But when we go for the post-transition elements like from manganese till zinc, they are not existing in their highest oxidation state in their halide form. Okay. So for manganese it is +4, and for iron and cobalt it is +3. And if you see for nickel, it is +2 only. Okay, in nickel dihalide, you see it is +2 only. Okay, and if we go for copper, copper is the only element which exists in +1 oxidation state, right? Yesterday also we have discussed in under oxidation state topic. So copper can exist in its +1 oxidation state. Okay, so which is the very, very lowest oxidation state. So in this case, so the X triple dash. X triple dash means it corresponds to chlorine and chlorine till iodine. Means chlorine, bromine, and iodine. So copper, CuCl, CuCl, CuBr, and CuI. CuCl, CuBr, and CuI. So only these three elements can exist in their +1 oxidation state for copper. Okay, so here the fluorine will not come. So the copper in its +1 oxidation state does not form fluoride, but copper 2 plus. If you look into for copper 2 plus, you see here copper is having +2 oxidation state, right? So here it is X double dash. X double dash means it is fluorine and chlorine. So copper at +2 oxidation state can form fluoride, chloride, bromide, etc. Okay. And bromide is also very rare only. And iodine will not undergo the reaction with copper. Got it? So these are the informations which you have to keep in mind regarding the halides of the 3D series. Got it? So what are the points you have to keep in mind? So titanium, vanadium, and chromium, they exist in their highest oxidation state with fluoride because of the highest bond enthalpy. Okay, manganese highest is +4 with halogen, and for iron and cobalt it is only +3, and for nickel it is +2. Copper in +1 state, it can form halides only with chlorine, bromine, iodine. Fluorine will not take place here. And in case of +2 compounds, so fluorine and chlorine, majorly they form +2 copper halides. Okay. And zinc, we all know about zinc. So zinc is zinc will exist only in +2 oxidation state, right? So zinc halide, like Ez10, it is X. X means from fluorine to iodine, all the halogen can form the dihalide with zinc. Ez10F2, Ez10Cl2, Ez10Br2, and Ez10I2. Zinc iodide. So all the halogen, fluorine, chlorine, bromine, iodine will form the dihalides with zinc. Got it? So this is about the higher oxidation state in halides. So guys, so do any of you have any doubt? Is everything clear? Next, we are going to study about the higher oxidation state in oxides. Shall I move on to oxides? Okay. The next tabular column which we are going to study is the higher oxidation state in oxides. So again, we'll take the first, the early transition elements oxides. Okay, from scandium till manganese we will take from group 3 till group 7. So here you can see that each element, scandium, titanium, vanadium, chromium, manganese. So all these 3D metal ions, they are existing in their highest oxidation state. What is the oxidation state of scandium in Sc2O3? It is +3. And for titanium, it is +4. Vanadium +5, chromium +6, and manganese it is +7. So it is gradually increasing from group 3 till group 7. Okay. So in Mn2 till Mn2O7, we have this gradual increase. But when you come to the post-transition series from iron, so what is the oxidation state of iron in Fe2O3? What is the oxidation state of iron in Fe2O3? Here in Fe2O3, what is oxidation state of iron? It is +3, right? So it is, it is +3. So +3, it is existing in its +3 oxidation state. So the highest oxidation state should be +7 for +8 for iron because it has 8 electrons in its valence shell. But the stable oxidation state is +3 for iron. And it is decreasing. For cobalt, it is again decreasing from for nickel, copper, zinc. For zinc and all, it is +2 only. Okay, it is +2. So it is decreased. So first it is increasing, then it is decreasing. Okay. Now, if we compare the stability of higher oxidation state in 3D series for oxides and fluorides, oxides will be more stable compared to fluoride. Okay. So I have two examples in front of you. So one is manganese oxide and the other one is manganese fluoride. So here both the compounds are having the 3D metal as manganese, but one is oxide and the other one is fluoride. So manganese is existing in its +7 oxidation state in its compound, and here it is +4. So when manganese is bonded with oxygen, then it is very highly stable at its highest oxidation state. But if it is bonded with halogen like fluorine, it is stable only at +4. So the higher oxidation states are stable for an element when it is bonded with oxygen. Clear for all of you? So oxides of 3D series are highly stable compared to fluorides. Okay. So what about others? Only Sakshi is replying. What about others? Sanjana, Sanika, two Sanikas, and Vaishnavi, Jyoti, Vikas, Suryakota. What about you guys? Is it clear to all of you? Are you all listening? If you are getting any doubt in between, you should not feel shy. Okay. Don't get scared to ask your doubt. Feel free to ask your doubt. We are here to clear your doubts only. So without understanding, please don't sit. Okay. So next, so here we are completing this standard electrode potential and oxidation and stability concept of the corresponding compounds. And the next general property is magnetic property. Okay. So there are three types of magnetic behavior for a metal ion. So in front of you, you are seeing a picture, no? A GIF kind of thing. So what do you observe from this? So we have the D block metal ions inside that bag, and I am bringing a magnet in closer to that metal ion. So that particular compound is getting attracted towards that magnet, right? So that the compound which is present inside that bag, so there are three nature. So a compound, a D block metal compound can have three types of magnetic behavior. Okay. So they are diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic substances means the one which gets repelled by the magnetic field. So if I bring the magnet in closer to the substance, it will not get attracted. They will get repelled. Okay, so those substances are called as diamagnetic substances. And paramagnetic means they will get attracted towards the magnetic field. So means the compound which is the metal ion which is present inside this bag is uh, paramagnetic. And ferromagnetic means it is the one which is getting very strongly attracted. One which gets very strongly attracted towards the magnetic field. So these are the three magnetic behavior of a D block metal ions. Okay. And how to find out the magnetic nature by seeing the number of electrons. So every time we will not do the experiment in the lab and we'll find out the answer. No. So if using a pen and paper only, we have to find out the answer, whether the given substances, given metal ion is paramagnetic or diamagnetic, etc., etc. So how to find out the diamagnetic character and paramagnetic character? So the paramagnetic character is directly proportional to unpaired electrons. If the number of unpaired electrons for a compound is more, then that particular compound is highly paramagnetic in nature. So let me take one example for you. So I have taken chromium. So chromium configuration is 3d5 and 4s1. So how many unpaired electrons I have here? I have 6 unpaired electrons for chromium. Yeah, yes, it is 6. So if it is 6 means obviously it is paramagnetic in nature, right? So what about for manganese? In case of manganese, you see the configuration is 3d5 4s2 and I have 5 unpaired electrons, but still the manganese is paramagnetic in nature. Okay, what about for zinc? Zinc with atomic number 30, the configuration is 3d10 and 4s2. Do we have unpaired electrons in zinc? Do we have unpaired electrons in zinc? No. Yeah, since it doesn't have unpaired electron or it has zero unpaired electron, it is diamagnetic in nature. So if the number of unpaired electrons are more, then the paramagnetic character is more. So if I compare chromium and manganese, so chromium is more paramagnetic in nature compared to manganese. Okay. So clear for all of you? So we will discuss some more information about this magnetic character in the next slide. Okay. So I hope this is clear. So now the next topic concept is, so this is the shell distribution for electrons for an atom. Okay, this is the electrons which are getting ferromagnetic. We will not study here in this lesson, my dear. So there are three magnetic nature for a substance. So I have told those three, but ferromagnetic we cannot find out by seeing the number of electrons. Okay. So that will come in solid state lesson, but unfortunately, solid state lesson is deleted. Okay, it is deleted from the syllabus. So we will not study in detail about the ferromagnetic substance. So only we will be asked to find out whether a given atom or the ion is diamagnetic or paramagnetic. Okay, Sanika? Yeah. So here I have electrons distributed in their respective shells from K shell, L shell, M shell, and N shell. So the outermost shell N shell has 2 electrons. Okay. So the movement of electrons can be about its own axis and about the nucleus. So what this electron can do? Electron can rotate about its own axis and it can rotate the nucleus like the earth is doing with the sun. Okay, so earth is rotating on its own and also it is rotating the sun, right? The sun is the nucleus here. So the electron is rotating about its own axis as well as it is rotating the nucleus. Got it? So because of this movement of electron about its own axis and about the nucleus, so each electron will be associated with a magnetic moment with it. Okay, so there is a magnetic moment associated with each electron. Okay, that is called as spin-only magnetic moment. That spin-only magnetic moment is represented by the letter mu. So this is called as mu. This is called as mu. Okay. The magnetic moment is denoted by the letter mu. And we have one formula to find out that magnetic moment. Okay. It is square root of n into n plus 2, where n is the number of unpaired electron. And the unit of this magnetic moment is Bohr magneton. Unit is Bohr magneton. So this is very, very important formula. Very easy, but it is very important. So they will give some ions, okay, and they will ask us to find out the magnetic moment for that particular ion. So how to find out that? So I'll give you one example. Okay, so let me take chromium. So let me take chromium 3 plus. So how to find out the magnetic moment for chromium 3 plus? Any idea? So we need to find out only the number of unpaired electrons. If we are getting that, we can find out the mu value. So how to get the number of unpaired electrons? By seeing the metal ion. So first you have to go for the general electronic configuration for chromium. So it is 3d5 and 4s1. And for chromium 3 plus, so we have to remove 3 electrons. So 1 electron from s orbital, yeah, and the other 2 electron from d orbital. So we will have 3d3 and 4s0. So totally how many electrons we have? We have 3 electrons in d orbital. Yes, Vaishnavi. So the number of unpaired electrons is equal to 3. So you have to distribute the electrons in 3d orbitals and then you have to check. So in 3d orbital, I have 3 electrons. So it is 3. Okay. So if I substitute the value of 3 here in the formula, what I will get? It is square root of 3 into 3 plus 2. 3 plus 2 is 5 and 5 into 3 is 15. Yeah. So square root of 15. Very good, Sanika. So that is the answer. Square root of 15 is the answer. Root 15 Bohr magneton is the value. You don't have to go for root 15 and all. Even if they ask you, it will be very easy only. So maximum we have only 5d orbital. If the number of unpaired electron is coming out to be 1, then 1.732 will be the answer. So if n is equal to value of mu, I am saying, okay. If n is equal to 2, then the answer will come in 2 point something. If n is equal to 3, you will get the answer in 3 point something. If n is equal to 4, it will be like around 4.90 kind of. Okay. And if n is equal to 5, it is 5 point again the same thing, 5.79. So if you take out the answer from this root 15 means the value will be around 3 point something Bohr magneton. So it actually represents the number of unpaired electrons only. Got it? So this is how you have to find out the answer. So they will ask this type of question and match the following type. Or once they have asked for only one metal ion, they have asked for chromium 3 plus only. Okay, so this is a very easy and simple question which will not consume time for us in the examination. Okay, shall I give you one more ion? Will you try? Shall I give one more ion for you guys? Okay. Okay. All of you do for nickel 2 plus. Do for nickel 2 plus. Find out the magnetic moment for nickel 2 plus. First of all, tell me how many number of unpaired electrons are present for nickel 2 plus. Nickel 2 plus has 3 unpaired electrons, Sakshi? No, yeah, it is 2. It is 2. So what is the configuration? Okay. Okay, I'll do this problem. Before that, you guys try to find out the magnetic moment first. Try to find out the magnetic moment. Then we will move on to the solution. Root 8. Okay, let's check. So the configuration of nickel is the configuration of nickel. The configuration of nickel is 3d8 and 4s2. And nickel 2 plus means it is only 3d8. 4 is 0. 3d8 and 4 is 0. And 3d8 means how many unpaired electrons? 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 unpaired electrons. So n is equal to 2. So root of 2 into 2 plus 2. So it will be root 8. Okay, it will be root 8. Yeah, very good. Very good, student. So this is a very easy, very easy question, which will give you 4 marks easily. So this type, don't leave this type of questions if you're getting in your examination. Okay, fine. So I hope the magnetic property and the calculation to find out the magnetic moment part is clear to all of you. So do any of you have any doubt? Shall we move on to the next general property? Yes, fine, fine. So the next is formation of colored ions. So you can see from titanium till copper, we have several test tubes containing different colored ions in their different oxidation states. So each oxidation state for a particular metal is giving different color. Like if I take vanadium, vanadium is existing in 4 oxidation states. So +2 is violet in color, +3 is green in color, +4 is light blue in color, and +5 is kind of yellow-orange color, right? So oxidation state, if the oxidation state is differing, then the color also changes. Means the color of a particular metal ion depends upon the number of electrons, number of electrons present in the d orbital. Okay, if only one electron is present, then the color will change. If 2 electrons are present for vanadium, then it will change. The same thing for other elements also. Okay, so the formation of this colored ion is mainly due to 2 reasons. The first reason is d-d transition. Okay, so the electron will jump from one d orbital to another d orbital. Okay, and only the elements which have the unpaired electrons can undergo this d-d transition, right? Otherwise, the electron cannot jump. The paired electrons cannot jump, no? So I'll show you the d-d transition. So you see here, so we have d orbitals, we have low energy d orbital and higher energy d orbital. So initially, electron will be present in the lower energy d orbital. So that electron, what it will do, it will try to absorb some energy which we are giving from outside. Okay, so this is that energy. So this particular electron is absorbing the energy which we are giving, and it is going to the higher energy state. Okay, from one d orbital to another d orbital, it is moving. It is this is called as transition. And the electron which is going to the higher energy orbital cannot stay in the higher energy state for long. If something is present in very higher energy state, it is unstable, right? So if a person is very angry, it means he is in its very higher energy form. The person cannot stay in its that form, that unstable form for long. So he or she has to come to the stable state. Means he or she has to come to the lower energy state. So in the same way, electron will also scandium in its plus 3. No, my dear, scandium will not show color because it's only stable status plus 3, right? All the 3 electrons will go away and we don't have electrons in the orbital. So DD transition cannot occur and scandium do not show any color. It is colorless. Clear, Sakshi? Yeah. Yeah, listen. So the electron which has moved to the higher energy d orbital, it will try to come to the lower energy d orbital again. So how it will come back? So it will emit the same amount of energy which it has observed, and then it will come to the lower energy d orbital. So how it will come down? It will emit out the energy which it has observed, and then it will come to the lower energy d orbital. And the radiation, that energy which is getting emitted out, so that energy frequency or wavelength will correspond to, or they will fall in the visible region of our electromagnetic spectrum. So do you guys have heard of electromagnetic spectrum before? Have you studied in your class 11 physics and or in atomic structure of class 11 of chemistry? You might have studied. Have you heard of this term, electromagnetic spectrum? Students, have you heard of electromagnetic spectrum before in your physics and chemistry, class 11? I don't know in which class electromagnetic spectrum is given for physics, whether it is given in class 11 or 12, but in atomic structure lesson of chemistry in class 11, we have this electromagnetic spectrum. Do you guys heard of it or not? So in that electromagnetic spectrum, we will have different regions, right? Visible region, infrared region, and ultraviolet, UV, X-rays, gamma rays, microwaves. Able to recall? Yeah. So that is called as electromagnetic spectrum, and in that we have one region called visible region. So the energy which is coming out by these electrons, that energy will fall in the visible region of that electromagnetic spectrum. And because of that only we are getting the color. Okay, VIBGYOR. We have VIBGYOR, no? Violet, indigo, blue, green, yellow, orange, red. According to that VIBGYOR, we will get color. Got it? But there are some exceptions for some compounds. I'll give you those exceptions. So these are those exceptions. Vanadium plus 5, chromium plus 6, manganese plus 7. So these 3 elements, if you observe, they do not contain electrons, unpaired electrons in its uh, highest oxidation state form. Like if you take vanadium, what is the configuration for vanadium? It is 3D, 3 and 4s2, right? Vanadium plus 5 means what is the meaning? So all the 5 electrons are lost. So the configuration is 3d 0 and 4s 0. So d orbital doesn't have unpaired electron, but still vanadium plus 5 shows some color. The previous slide I showed you, no? It showed some yellow orange kind of color, vanadium plus 5. So what is the reason for showing colors even though it doesn't have unpaired electron? It shows color due to charge transfer mechanism. Due to charge transfer. So suppose if vanadium is bonded with if V2O5 means here the oxidation state of vanadium is plus 5. So the charge is nothing but electrons. Electrons will move from oxygen to vanadium and it will show the color. Got it? So in both the cases, the electron movement is happening. Electron movement is happening. So a compound, a D block compound shows color due to two reasons. One is DD transition and the other one is charge transfer. So DD transition is because of the presence of unpaired electron. Charge transfer will come into the place where we don't have d orbitals electrons. Got it? Clear for all of you? Any doubt? Okay. So this is about the formation of colored ions. So this is one of the very special and unique character of a D block elements. Okay. Only D block metal ions will show colors. We have S block metals, we have P block metals, but those metals compounds will not show any color. Only the D block metal ions will show color due to the variable oxidation state. Okay, so this is one of the special character. And the next property is the formation of complex compounds. The next general property is the formation of complex compounds. Complex compounds or coordination compounds, both are same only. So what is the complex compound? So you can see in the picture that at the center we have an atom and that atom is the metal, D block metal. And ligands are surrounded. Ligands are surrounding this metal. How many ligands are there? Can you count and tell me how many ligands are present around this metal atom? So this is one ligand. And here we have another ligand. So how many ligands are there around this metal? Very good. It is six. We have, yeah, six. We have six ligands around this metal. So ligand can be anything. Ligand can be H water, ammonia. So we have many ligands. Cyanide, Cn minus, okay, CO. So we have many types of ligands. And I will discuss and I will teach you what is meant by a ligand and what is meant by a metal atom. Those things in the coordination compounds lesson. Okay. In that lesson, we can discuss these compounds in detail. But here, D block metals have the capacity to form this complex compounds. Okay. So the reason for that we are going to discuss here. Okay. So the reason for the D block metal ions to form this complex compound is due to smaller size, high ionic charge, and availability of vacant d orbitals. So if you take the metal atom, mostly the D block metal ions will be very, very small in size. Okay, not mostly in all the cases. And the charge, it can take the highest ionic charge, right? Like it can go till, manganese can go till +7, and iron can take +2, +3. So they can have different types of ionic charge. Okay, so in most of the cases, many elements will have their highest ionic charge. So that is the second reason. And the third is availability of vacant. Vacant means empty d orbital. So if something is empty, the one which is having the electrons can donate that electron to this empty d orbital and form the bond. So mostly the ligands are electron rich. Ligands will have the electron, more electron density. It is an electron rich compound. So that ligand will come with its electron and form the bond with this empty metal d orbital. Okay, so in this example, you can see. So we have iron. So here iron is in +3 oxidation state and here iron is in +2 oxidation state. Okay, so you all know how to find out oxidation state for complexes, right? We have to take this iron as X and for each cyanide it is -1. So -6, which is equal to charge on the complex, -3. So X will be -3 + 6. So it is +3. The same way here also. x minus 6 is equal to minus 4 and x is equal to minus 4 plus 6 is plus 2. So this is how I have calculated the oxidation state for the iron in both the compounds. Okay. So iron is the central metal D block atom here. So this is the iron atom and 6 Cn minus, they are surrounded to this metal atom. So iron can able to form the complex compound because of its very small size, high ionic charge and availability of empty d orbital. Got it? So you should not forget the three reasons for the formation of complex compounds. So is it clear? Zinc form complex. Yes, my dear. Zinc also will form complex compound. Ligand has oxidation state -1. Yeah. So we have many different types of ligand. We have neutral ligand. We have negatively charged ligand. We have positively charged ligands. So here this cyanide will come under negatively charged ligand. So for each cyanide, the charge which we have to give is -1. Okay. Suppose if I take a neutral ligand, H2O is a ligand, neutral ligand. The charge for neutral ligand is 0. Got it? So like this, we have a list of ligands. So those lists I will discuss in coordination compounds lesson. Don't worry. Okay. That time you will get clear that which how charge has to be given for which ligand. What charge has to be given for what type of ligands. Okay. Don't worry. And zinc will also form complex. Like I'll give you an example. Zinc Zn Cl4 2 minus. ZnCl4 2 minus. So what is the oxidation state of zinc here? It is X. And for chloride also it is -1 for each chlorine. So -4 which is equal to -2. So X is equal to +2. So zinc is existing in +2 oxidation state in this coordination compound. Okay. Vaishnavi, is it clear? Yeah. So this is how the D block metal ions, metal atoms are forming the coordination complex. They have this unique behavior. Then the next property is catalytic property. The next is the catalytic property of the D block metal atom. So every reactant will be converted into their corresponding products, and in that we will use some catalyst. So that catalyst in most of the reactions, if you see, we will use the D block metal atoms only. So why? Why we are using the D block metal atoms as the catalyst in many reactions? The reason is due to the multiple oxidation state that it is taking. So each D block element, if you see, they can exist in their multiple oxidation state, right? So because of this reason only, we are using the D block metal atom as the catalyst. For some reactant, if a particular reactant wants to have +3 catalyst, then that particular element, D block element, can exist in +3. If something wants +2, then since the catalyst D block metal ion which is present there can exist in both +3 and +2, if the reactant needs +2, so that can exist in +2. So because of the multiple oxidation state that a D block element can take, they can able to form the complexes and they can able to act as a catalyst also. So these are some of the examples. Haber's process, contact process. So Haber's process is used for the manufacture of ammonia. So N2 plus 3H2, okay, will give 2NH3. So for the manufacture of ammonia, we will use the finely divided iron as the catalyst. Okay, iron as the catalyst. So iron is the D block metal here. And in contact process is used for the manufacture of sulfuric acid actually. So in that we have 3 steps. So in one of the among those 3 steps, we will use the vanadium metal as the catalyst. So vanadium is present in its oxide form. So here vanadium is a D block metal. Okay. So for many manufacturing process, for many compounds manufacturing process, we are using the catalyst. So what is the role of the catalyst, my dear students? Role of the catalyst is to alter the rate of the reaction, right? So the role is to alter the rate of the reaction. It will speed up the reaction. So if a reaction is happening in 2 days, then this catalyst will make that reaction to happen in a single day or within half a day. So it will speed up the rate. So the D block metal atoms are acting as a catalyst in many of the reactions because of its ability to adopt the multiple oxidation state. Clear to all of you? So this is the very important point. This is the reason. Okay, take down. Take down in your meeting. Yes. So this is enough for today, my dear students. So we have studied many property, catalytic property, and formation of colored ions, formation of complex compounds, and some of the stability and magnetic property I have discussed. So we have discussed many general properties today for the D block elements, and also we have some more, the formation of interstitial compounds, alloy formation. So those things we will discuss in the next class. Okay, so any doubt from today's session for anyone? Is everything clear for all of you? So every day you guys have to study. Okay, don't just listen to the class and close your book. So every day, at least give some time to study each subject. Got it? Okay. Okay then. See you all in the next class. Take care. Bye bye. Thank you.